In this lesson, we're going to cover sequences. Our definition for a sequence is a list of numbers written in a definite order. Here's our notation. We have set notation, and then it says a sub 1 comma a sub 2. So these are going to be the terms in the sequence, or the sequence will be written in a formula where a sub n is listed right here. Or you may even see it like this, where it says what number you're starting to plug in with, and then you go to infinity. And then it says right here, a sub 1 would be the first term, a sub 2 is the second term, and then this would be the nth term. An example of a sequence is a Fibonacci sequence. In order to find a Fibonacci sequence, you take the two preceding terms, you add them together, and it gives you the next term. So it starts 1, 1, and then 2, and then 3. You add these to get 5, add them to get 8, and so on. This is also known as a recursive sequence. So a recursive sequence is any sequence where you need a previous term to get to the next term. Our next definition says a sequence, and then it's in set notation where it says a sub n, has the limit L written as the limit as n goes to infinity of a sub n equals L, or a sub n approaches L as n approaches infinity. And this will be the case if we can make the terms a sub n as close to L by taking n sufficiently large. If the limit as n goes to infinity of a sub n exists, then we say that the sequence a sub n converges, or it is convergent. Otherwise, the limit will not exist, and then we would say that the sequence diverges or is divergent. Here we have a list of our limit laws for sequences. It says we have one sequence a sub n and another one b sub n. They are convergent and c is a constant. If that's the case, then we have these limit laws. If you have the limit as n goes to infinity of a sum or a difference, you can split it up and do the limit of the first sequence plus or minus the limit of the second. If you have a constant c, you can pull that c to the front, and then you take the limit of just the sequence. If you have the limit of a product of sequences, you can do the product of their individual limits. If you have the limit of a quotient of sequences, you can do the quotient of their individual limits. And then finally, if you have the limit of a sequence to a power, you can pull the power to the outside and take the limit of the inside sequence. Here we have the squeeze theorem. If you have three sequences where b is in between a and c, and the limit of a is equal to the limit of c, which equals L, then because b is in between, then you conclude that the limit of the sequence b is equal to L as well. So here's a diagram that demonstrates this. We have the sequence of a sub n down here. We have the sequence of c sub n up here. And then it says that b sub n is in between those two sequences. You can see b is in between. So it kind of squeezes the sequence for b in between a and c. Here we have a few more theorems and definitions for sequences. If the limit as n goes to infinity of the absolute value of a sequence equals 0, then the limit of that sequence will also equal 0. For L'Hopital's rule, if you have a sequence that's of indeterminate form, 0 over 0, or plus or minus infinity over infinity, then taking the limit of the quotient is the same as the limit of their individual derivatives. Here we have a note. It says the sequence r to the n, so something of the form r to the n, is convergent if r is between -1 and less than or equal to 1, and divergent for all other values of r. So the limit as n gets larger and larger of that sequence, specifically of the form r to the n, where again r is going to be the constant. This limit will equal 0 if r is between -1 and 1. This limit will equal 1 if r equals 1. So here we have two diagrams. So first, if r is equal to 1, it would be 1 to the n, which as you plug in bigger and bigger numbers for n, that r will still be a height of 1. So the sequence will just continue at a height of 1. Next, if r is greater than 1, as you raise a number that's greater than 1, to a higher and higher power, then the terms will get higher and higher. And then finally, if you have a value for r, so a number between 0 and 1 like 1/2, and you raise it to the n, as you plug in larger and larger numbers, the terms are going to get smaller and smaller and closer to 0. And this diagram demonstrates the same sequence, but r is less than 0. So we have two situations. Either r is less than -1, so like -2 or -3. If you take those values and you raise them to higher and higher powers, what's going to happen is the terms are going to oscillate, meaning they're going to flip from positive to negative and positive to negative, but they're going to get bigger and bigger in the positive direction and bigger in the negative direction. But if you have a value for r that's in between -1 and 0, like -1/2, the terms are still going to oscillate from positive to negative, but they're going to get closer and closer and closer to 0. This definition says a sequence a sub n is called increasing if each term is getting bigger than the previous. You can see that right here. A sequence is called decreasing if the terms are getting smaller, so the next term is smaller than the one before it. A sequence is called monotonic if it is either increasing or decreasing. Then we say that a sequence is bounded above if there is a number m such that that value is bigger than all the terms in the sequence. It is bounded below if there's a number lowercase m where the lowercase m is less than or equal to all the terms in the sequence. If a sequence is bounded above and below, then we say that it is a bounded sequence. And then finally we have the theorem monotonic sequence theorem. Every bounded monotonic sequence is convergent. This example says list the first 5 terms of the sequence. So here's our sequence. It's 3 times -1 to the n, all divided by n factorial. So first we're going to find a sub 1. That means we're going to plug in 1 for n. So in the numerator, this will simplify to -3, and then 1 factorial equals 1. So -3 divided by 1 is just -3. Next we're plugging in 2 for n. So -1 squared is just 1, so the numerator becomes 3. And to find 2 factorial, remember for factorial you start with this number and then you multiply down to 1. So we go 2 times 1 is 2. So next we plug in 3 for n. This is going to make the numerator -3. And then down here we have 3 times 2 times 1. So the 3 and the 3 will cancel, so we end up getting -1 over 2. When we plug in 4 for n, this is going to be +1, so we just get 3 in the numerator. This represents 4 times 3 times 2 times 1. So the 3 in the numerator will cancel with the 3 in the denominator, so all you have left is 1 over 4 times 2, or +1/8. And then finally, when we plug in 5 for n, this is going to make -1, so we get -3 in the numerator. This will be 5 times 4 times 3 times 2 times 1, so the 3's will cancel. So then you multiply 5 times 4 times 2, and you get 40. So here's the first 5 terms of this sequence. We have -3, 3 halves, -1/2, 1/8, and -1 over 40. For part B, we have a sub 1 equals 4. A sub n plus 1 is equal to a sub n divided by a sub n minus 1. So this is going to be a recursive sequence because to find this term, you're using the term before it divided by, again, the term before it minus 1. So we're already given a sub 1 is 4. According to this formula, to find a sub 2, we're going to take a sub 1 here, and then subtract 1. So again, to find a sub 2, we're plugging in a sub 1 here, and then we subtract 1 in the denominator. So we end up getting 4/3. To find a sub 3, we're taking the term before it, which is 4/3, and we're plugging that here and here. So now we're just going to simplify this. Down here we have 4/3 minus 1, so that's the same as 4/3 minus 3/3, or just 1/3. And 4/3 divided by 1/3 equals 4. To find a sub 4, we use the term before it, so this just becomes 4/3. And you'll notice we already had 4/3 back up here for a sub 2. So when we took this, plugged it in, we just got 4. So that means that a sub 5 will just be 4. All right, so let's go ahead and write this all out. So here's the first 5 terms of this recursive sequence. This example says write a formula for the general term a sub n of the sequence, assuming that the pattern of the first few terms continues. So for part A, we have 1/3, 1/9, 1/27, 1 over 81, and so on. And I made a note over here, this is a geometric sequence. And just to refresh our memory, a geometric sequence is one where you take one term and you times by a value to get to the next term, and you times by the same value to get to the next term. And so you can see that the common ratio, the number we're timesing by each time, is going to be 1/3. So we note that as r equals 1/3. And we want to write a formula for the general term, or a sub n. So we're going to write it as 1 over 3 to the n, where to get the first term, you're going to plug in 1 for n, so that makes 1/3. For the second term, you plug in 2 for n, so that's 1 over 3 squared, or 1/9. And for the third term, you plug in 3 for n, so it's 1 over 3 cubed, which is 1 over 27. We can leave our answer like this, or it can also be written as 1/3 raised to the nth power. For part B, we have the sequence 7, 4, 1, -2. This is an arithmetic sequence, and the common difference is -3. So what you do is you start with the first term and you add a -3, and that gives you the next term. Add -3 again, that gives you the next term. So again, that works for an arithmetic sequence. And when you're writing the formula for an arithmetic sequence, you identify the number you're adding each time, which again in this case was -3. And then you take -3 and you times it by the variable n. And then if we were to plug in a 1, this would make -3. So we need to think, what would we add to that to make this first term? So that would be plus 10. And let's just double check. When we plug in 1, you get -3 plus 10, which is 7. To get the next term, we plug in 2, so that makes -6 plus 10, which gives you 4. Plug in 3 for the third term, you get -9 plus 10 makes 1, so it works out. So here's our formula for this sequence. This example says determine whether the sequence converges or diverges. If it converges, find the limit. So for part A, we have the sequence a sub n equals n plus 1 over 3n minus 1. So what we're going to do is we're going to take the limit as n goes to infinity of this sequence. So we have the limit as n goes to infinity of n plus 1 over 3n minus 1. So we have the limit as n goes to infinity of n plus 1 over 3n minus 1. Since this is an infinite limit, back when we originally did these problems, what we did is we looked at the highest power in the denominator, which is n to the 1, and that's what we divided the numerator and denominator both by. So we're timesing by 1 over n divided by 1 over n. Next, we take this expression, distribute to both terms on top, and then also in the denominator. And then at this point, we're taking the limit of the numerator and the limit of the denominator. When we take the limit of the numerator, the limit of 1 is just 1 because it's a constant. The limit of 1 over n, as n gets larger and larger, this fraction is going to go to 0. In the denominator, when we take the limit of both of these terms, the limit of 3, because it's a constant, is just 3. And the limit as n gets larger and larger of 1 over n also goes to 0. So we end up getting the value 1/3. So since the limit as n goes to infinity of a sub n exists, because we got a value, the sequence a sub n converges. For part B, we have a sub n equals cosine of 2 over n. So we're going to start by taking the limit as n goes to infinity of the sequence. At this point, because we're taking the limit of a composition of functions, we're going to use a theorem from a previous chapter where it says that we can pull the outside function to the outside of the limit. So we get cosine of, and then it's the limit as n goes to infinity of 2 over n. So I pulled the 2 to the front of this limit, and then as n gets larger and larger, this fraction is going to go to 0. So 2 times 0 will just be 0. So we have cosine of 0, which equals 1. So I wrote it out. Since the limit as n goes to infinity of a sub n exists, because we got the value 1, the sequence a sub n converges. For part C, we have the sequence ln of n over ln of 2n. So first step, we're going to take the limit of the sequence. So next we're going to manipulate this, and we're going to expand the denominator. So we have ln of 2 plus ln of n. And next, the technique we're going to use is we're going to divide the top and bottom by the dominant term that's in the denominator. So this would be the dominant term, ln of n. And then next, we're going to take this and multiply it on top and then distribute it in the denominator. So here we can take the limit of the top and the limit of the bottom. So the limit of 1 is just 1, so you can see that that is here and here. And then for this term, I brought the ln of 2 to the front of the limit because it's a constant. So then we just have the limit as n goes to infinity of 1 over the natural log of n. So here's your graph for the natural log. As n gets larger and larger, the height of the graph is just going to grow without bound. So since it's 1 over the natural log of n, as n gets larger, this fraction is going to go to 0. So we end up getting 1. So since the limit of this sequence exists, we got 1. We say that the sequence converges. For part D, we have a sub n equals n factorial over 2 to the n. So when we look at this sequence, you have a factorial on the top and you have an exponential in the denominator, so there's nothing that we can really manipulate. So I just wrote a note, we're going to look at the terms to try to find a pattern. So first we're going to plug in 1 for n, and you just get 1/2. Next, we plug in 2 for n, so we get 2 factorial over 2 squared, and that reduces to 1/2. Then we plug in 3, so we get 3 factorial over 2 to the third. This represents 3 times 2 times 1. This would be 2 times 2 times 2. So the 2's on top and bottom will cancel, and we're left with 3/4. When we plug in 4, we have 4 factorial over 2 to the 4th. So when we write both the numerator and denominator out, you can see that a set of 2's will cancel, and then this 4 will cancel with 2 2's, so we're left with 3/2. So we're going to plug in a couple more to see if we can identify a pattern. So we get 5 factorial over 2 to the 5th, and at this point let's start canceling out the 2's, and then 2 2's will cancel with the 4, and we get 15 over 4. So finally we're starting to see a big jump. Let's do one more just to double check. So plugging in 6, so we get to here, let's go ahead and reduce, and we get 45 over 4. So you can see from the 5th term to the 6th, there was also another big jump. So since the terms are growing without bound, we conclude, therefore, the sequence a sub n diverges. All right, guys, thanks for watching.